This video is going to serve as a supplement to the lecture that we did in class to discuss three of Kepler's laws. So the premise for this is Johannes Kepler was in the 1600s. He and his trusty sidekick Tycho Brahe assembled a whole bucket load of data to map out the celestial bodies that they observed in the heavens. They didn't know why things did what they did, but they collected a whole bucket load of data, and they came up with three laws that basically empirical data that supported their conclusions. It wasn't until Isaac Newton came along with his universal gravitation laws that he could explain the why behind Kepler's laws. So the first thing I want you guys to be able to explain is that his first law, which is all orbits are elliptical with the sun at one focus. So what we have assumed in class so far are all circular orbits, which is fine for our kind of baby physics treatment of celestial bodies, but they actually all are elliptical. The PhET sim that I had you guys look at class, there's a link to it on Canvas if you want to play around with that again a little bit more. So we want to see what happens if we have a circular orbit and then we increase the speed and decrease the speed. Basically, what is the relationship between the speed and the location of the satellite? So we're going to do an increase and a decrease. So the sim, first one, at this point right here, you increase the speed, and what happened to that orbit? Well, it became elliptical. So if the sun started at the center of the circle, this right here, when this happened, this would basically cause, if we look at our equation for centripetal force, okay, if our velocity was getting to be too big, we've increased the speed, well, it can't maintain that circular motion, so this satellite is actually going to go past and beyond the circle out here. So it's going to become elliptical, but it doesn't trace out the circle and then become an ellipse. It really becomes an ellipse touching on that point only. So I'm going to try to make it touch just that point. So it's going to shoot past the sun. It's going to begin to slow down, and then the Earth's or the sun's gravitational pull is going to pull it back in. Oops, so we have that coming back in. That's a pretty good ellipse. And again, it just touches at that one point. So the sun is at that near foci of where the satellite is the fastest. The other foci would be over here. We call this the perihelion position. And over here, this would be the aphelion. And my sketch isn't that great, but you could certainly look it up. So that's what happens when we increase the speed. The second premise here is what happens if we decrease the speed. Well, if we think again about circular motion, it doesn't have enough speed to maintain that circular orbit, so it's going to start to fall into the sun. So as it begins to fall into the sun, because it's getting closer to the sun, the force is increasing, which actually causes it to speed up. So it's going to get a new elliptical orbit, and that's not such a great ellipse. Kind of looks like an egg, but doing my best here. Okay. Again, it just touches at that one point there, the new orbit, and then the foci would be here. So here, where the satellite is moving the slowest, would be its aphelion position. So it's furthest away from the focus in that position. So this is basically Kepler's first law. So second up is looking at Kepler's second law, which we won't spend a lot of time with, but it is basically the idea of equal areas in equal times. Since we've discovered that the satellites or the planets will change their speed, they'll be the slowest at the aphelion and the fastest at the perihelion. If I take a line and draw it from the foci to the trace of the orbit, as it sweeps out, or as it clocks out equal amounts of times, it will sweep out equal areas. So that area would equal the area swept out in that amount of time. So that's all there is about equal areas on Kepler's second law. We won't spend a lot of time discussing it. All right. Kepler's law of periods is the one that we actually spend a lot of time discussing. We've already kind of derived some of these things just on the worksheets that we've worked on before. But Kepler basically came up with this idea that if I take the ratio of the period squared to the orbital radius cubed, that's going to be equal a constant. So this, r, is the distance from the satellite to the central body. And that central body is called the parent. So what do I mean by this? That means if I have the Earth orbiting around the sun would be the parent and the Earth would be the satellite. And basically what Kepler discovered is that he did the same ratio for, say, Jupiter or Mars or Mercury. That ratio of t squared to r cubed would be the same for all the planets, as long as they had the same parent, or the sun, at the center. Again, he didn't know why. It took Newton's law of universal gravitation to figure that out, but we'll show you where it all came from. So, once again, Newton's second law says the sum of the forces is equal to the mass times the centripetal acceleration. Big G will make big M to be the mass of the parent planet. Little m will be the mass of the satellite. That will be the orbital distance, is equal to mv squared over r. And again, this is the mass of the satellite. So again, we're going through the same algebra that we've done in class before. That m is going to cancel with that m, that r cancels with that r, and I get big G times the mass of the parent, r, is equal to v squared. Now, we're going to get this in terms of the period, so we're going to set that equal to 2 pi r over t, square the whole thing, and now we're just going to use these two parts right here and multiply everything out. So you get G, big M, R is equal to 4 pi squared r squared over t squared. Now I'm just going to cross multiply, and I get t squared gm is equal to 4 pi squared r cubed. And now we can see we can get that ratio of the period to the orbital radius, and I get t squared over r cubed is equal to, more specifically, 4 pi squared over gm, where this again is the parent and this would be the orbital distance or orbital radius. So again, that ratio for any planet that has a common parent is going to be the same. It'll be 4 pi squared g over m. So how are we going to apply this? Well, there are two different things that we will look at with Kepler's laws, or that you should be responsible for. One application, again going back to Kepler's idea, that if I take the ratio of the period to the orbital radius cubed, and again let's assume this is, say, Earth, that's going to be equal to the period of some other object that has a common planet over that object's orbital radius cubed. So let's say this would be Jupiter, but it really could be anything. Those two things will be equal to each other. So if I know three of them, I can get the third one, and I don't have to go through this big, hairy, nonsense derivation in order to get there. If I just kind of remember that ratio, Kepler's second law, I can get to it really quickly. And that's kind of the big idea and why it's important to know. Always helpful for multiple choice. So this is useful for our solar system. This could be the Earth with all the artificial satellites that orbit the Earth. In that case, the Earth would be the parent. Or we could apply it to Jupiter. Has 3 or 4 moons that orbit it, I believe. So Jupiter could be the parent planet, and then it has its own moon. So these are just different ways that you could apply it, and you might see it. The second way, which we're going to do in class, is looking at a more graphical representation. AP loves a good graph. But this idea of that ratio, if it's a constant, then if I graph the period squared versus the radius cube for a whole bunch of different planets, say all 9 planets, including Pluto, we'll include Pluto, in here, we should get a direct relationship, and the slope of that line should represent what was constant, which would be the 4 pi squared g over m. And again, that would be the parent mass. So we're going to do this in class and just kind of practice that out and go through whole that derivation. So that is the conclusion of Kepler's 3 laws.